Okay, folks, welcome back. It occurred to me I shouldn't have erased the board. I should have taken a picture of it, but I guess you have a video. I did rewrite the formal definition of limit up there. And let's just work with it. I want to draw another picture of, say, this sequence. A sub n is the sequence 1 minus 1 over a. And so we just want to work with the sequence, and the first term, let's see, it would be 1 minus 1 is a zippo, the second term is a half, the third term, 2/3, 3/4, 4/5, etc., 5/6, 6/7, etc. And so that's that sequence, and I just wrote down a whole bunch of terms there, and it appears that it's going to converge. I mean, this looks like it's headed towards 1, and in fact it is. And we'll use this formal definition just to show a picture of what we're talking about. Okay, here's a coordinate plane. That's the y-axis, and here's the x-axis, and there's 1, 2, 3, 4, 5, 6, etc. And so now I'm going to plot these points. There's 0, 0. Here's 1, 1/2. 2, 2/3. 3, 3/4, etc. Here's the line y equals 1. And if we imagine that line extending forever, what we're saying is we can choose any arbitrary distance right there. We can make it as big or as small as we want. And eventually these dots will be within that interval. So as a picture, we'll make that L plus epsilon. Down here is L minus epsilon. And here's the interval in question. And all we're saying is that no matter how big this interval is, no matter how small it is, our sequence will be within that interval at some arbitrary large point, and it will stay within that interval for the remainder, till forever. So, and that's a picture. That's intuitive. Now, of course, we want to prove these things. So let's prove. Say 1 over n squared converges to 0. Converges. And of course, by limit theorem, we know this is to 0. So we want to prove that that converges it to 0. And in order to do that, we're given, for every given, any epsilon, let's do for every epsilon greater than 0, there exists an n, which is an integer, by the way, trivial for, these are sequences, so n's an integer, such that excuse me, 1 over n squared minus epsilon is less than L. Minus L is less than epsilon. Nicely done, Brett. And L in this case is 0. So 0, another property of erasure. So we want to prove that. So all we're going to do is work some algebra. Because we want to pick something in terms of epsilon that we can let n be larger than. So I'm going to just work some algebra. This 1 minus n squared is less than 0. Minus 0 is just 1 minus n squared. So just working algebra. Don't need the absolute value signs because they're both positive. And because they're both positive, I can multiply both sides. 1 minus epsilon, n squared. Oh, yeah, let's do that. And then take the square root. 1 epsilon square root less than n. And there you have it. Choose n, capital N, to be greater than the square root of 1 over epsilon. Then, that you're just working backwards. If you choose this, then that's true, that's true, that's true, and finally that's true. Just work backwards. So that's a proof. Please note, I don't care how small epsilon is. Let's say it's 1 over 100. If that's the case, then this square root, 1 over 100 is 100, square root of which is 10, and is bigger than 10. Suppose epsilon's 0.00000. It doesn't matter how small. It doesn't matter how small as long as we take the reciprocal of it, which will be a huge number, by the way, and then the square root, and let n be bigger than that. That is proven. Okay, now erase. We can generalize this, actually. Power series are coming. And we can actually generalize this to 1 over n to the p. You know, we can show that that is the same. I have that finished. It's relatively trivial with that. Choose n to be, I'll leave this to be an exercise. Choose n to be, whoops, where are we? Square the pth root of 1 over epsilon. And then it'll follow. Everything will fall back into place. And these two are closely related. That's why I didn't do that proof formula. I would just like to do the properties, and then that's it for us today. These are pretty simple because of the same thing as properties of limits. Properties. The limit of a sequence A sub n plus B sub n is the limit A sub n plus B sub n. Whoops, sequence. Plus n minus, of course. You can add them, you can add and subtract them. The limits are the same. Oops, this is plus and minus the limit. And then you can multiply them. And divide, of course, would have to be not equal to 0. Limit over b exists. Those are the properties. So all we're saying here, limit theory works just like, convergence theory works just like limit theory. And I just want to point out one thing to you, give you a little example, and then we'll pack it for today. Whoops, that's okay. Example. So the limit as n goes to infinity, I'll do 3n squared. 3n squared over n squared plus 2n minus 1. Something like that. You remember the trick where we're dividing everything by n squared? This is equal to 3n squared over n squared over 2n over n squared plus 1 over n squared. And as you take the limit, this becomes 3 over 1. Remember, the highest degree, I just wanted to let you know because there's, I think, 2 homework problems that regard that. Hey, expect to hear from me whatever day you see this. Right now, it's Tuesday. And hopefully today I'm putting up a PowerPoint in terms of logistics. Hopefully that's up. You have any problems? I think I showed them to you. Good luck. See you next time.